Hello, friend. My name is Derek Harder, and in the next set of videos, we're going to be looking at the fundamentals of machine learning through the context of how neural networks do machine learning. So we have a couple of different topics. So for one, we're going to be talking a lot about the central problem of machine learning, which is overfitting. And some of the mechanisms in general for machine learning, but specifically to neural networks of how you can fight overfitting. And we want to talk a little bit about how neural networks work, so kind of a theoretical or conceptual view. So talk a little bit about the so-called manifold theory of of neural networks, representations, and problem-solving abilities. So with that, let's go ahead and get going here. Okay, so we're first going to talk in this lecture video. We're going to be concentrating on generalization. Okay, so this is really about overfitting and how you fight it. So the the fundamental issue of machine learning is this tension between optimization and generalization. Okay, so as we've already seen in a couple of examples, after just a few epochs of training, performance on never before seen data starts to diverge. Okay, so we say that the model is starting to overfit at that point. And this is particularly a problem for neural networks because neural networks can be made as powerful as you want in order to overfit any problem. And it's very easy to make a neural network with millions of free parameters, which will be able to overfit most any kind of data, even just random noise. Okay, so optimization refers to gradient descent. So it refers to the process of adjusting the model to get the best performance possible on the training data. But at a certain point, a model is going to not be learning things that are useful for solving the problem in general, right? So it will overlearn on the noise or the ambiguous features of the data it's being trained with, and it won't be able to generalize. The performance for data it hasn't seen before will suffer on that. Okay, so a little bit more about that idea of underfitting and overfitting. So on the right-hand side over here is a typical learning curve, as I'll usually refer to it. Okay, and this is usually what it looks like when overfitting is happening. Okay, so for the first part of the training cycle over here on the left-hand side, the training loss. So we're showing both the training loss and the validation loss happening. And so they both will usually go down together at about the same rate. But at some point, they'll diverge, okay? So at some point, the training loss will continue to decrease on the data that the machine model, the neural network is being trained with, or whatever machine learning mechanism you're using. But the validation loss will stop improving. Yeah? So here, minimum or smaller loss is better. So it'll stop improving. It'll start getting worse and worse. So that's a classic sign that overfitting has begun. Right? Eventually, especially for neural networks, this will always happen. Generalization will stop improving, and the validation metrics will stall and then degrade. So when the model is overfitting, it's learning patterns that are specific to the training data. We don't want it to do that. So it's particularly likely to occur when your data is noisy, it has uncertainty, it has rare features. It's particularly likely to occur with neural networks. They always have plenty of power to overfit. So we're always fighting that. We're always trying to find the balance between optimization, but able to generalize well on problems. So just a little bit about what we mean by noise and training data. So there are different things that can cause noisy data. So for one thing, your data can be ambiguous or invalid. So like in the top figure here, these are some weird samples. It's hard to tell what those actually are, right? So unlike the ones on the bottom here, these are, they look like we could probably tell what they should have been. Like, for example, this one right here. but the data is probably clearly mislabeled in the MNIST data set, right? So somebody said this was a 4, it was actually a 7, right? So for one, I mean, for real data sets, I mean, there's so much. There's always going to be both, examples of both types of this noisy training data in there. So there'll be stuff that's mislabeled, and there'll be stuff that nobody would really be able to agree what the label should be for things like that. So the point being for this kind of noise is that if a model goes out of its way to incorporate such outliers, its generalization performance is going to degrade. So as an example of what we usually mean by that, so on the right, if you have a model that's overfitting, it's often doing something like this. So it's going out of its way in order to change its decision boundary so that it will correctly classify everything possible, right? So in this case, this looks like we're doing like a binary classification problem, and this is supposed to represent the decision boundary. And in this case, we might be overfitting. So these pointers here might be outliers. They look mostly like outliers, right? So on the left is what is most likely a more robust decision boundary, right? So, it can actually be better in terms of generalization, assuming that these points are maybe misclassified or they're outliers, that we kind of ignore things like that and instead try and make a model that's simpler. So in that case, usually simpler will generalize better. So something like this, where you have a smoother decision boundary, is often what you're trying to do with some sort of regularization method or something that's trying to fight overfitting from happening. And again, not all noise comes from like outliers or mislabeled data. So, I mean, sometimes things are just ambiguous, like the first example on the slide before. So in that case, what you'll see is things like this, where you've got large areas where there's a bit of a mixing, right? So most likely the things in those areas, the samples, there's really no clear decision even by experts whether they belong to the dark class or the light class here, right? So again, a model that overfits, that goes out of its way, it becomes very wiggly, and to try and get everything perfect on the training data, this model will actually have worse performance than a more general model on data it's not seen before. Okay. So, for example, one source of problem. So if you have data sets that include rare features, those are highly susceptible to overfitting, but spurious correlations are present even in noise. Okay, so you can see that from this example of training on MNIST. So in this case here, we're going to use the MNIST data set that you should be familiar with, but we're going to concatenate on, in one case, for one of these, we're going to concatenate on just random noise, right? So we take the original 784 actual pixels and add in another 784 additional with noise. And for the second example, we do the same thing, but we add in just zeros, right? So, the zeros are easier to ignore, but the noise, as you'll see here, the model will actually find correlations on that if you train it with a big enough model long enough. So let's go ahead and try that out here and see what it does. So in this case, we're going to do two training fits on this exact same model with 512 units in the dense layer. And we'll see how the accuracy is affected by, on the one case, having something with half of it as noise, and on the other case where we just appended a bunch of zeros. So there's not a lot of spurious correlation. So let's go ahead and train this. Take a little bit of time. So if you look at the typical outputs from these two networks, so all we're going to do is compare the validation accuracy. So we're using accuracy for our metric here of the one that was trained with some additional noise and the one that was trained with the same amount but all zeros. So you'll typically see this kind of result that the one with noise in the channel has a much more difficult time. It'd be 1 to 3% less accurate over training epochs. Okay, and that is significant for this amount of accuracy that we have in the thing here, and that's purely effect of the spurious correlations that this model here with the noisy channels added to it is finding in the data. Makes the task much more easier to overfit and find random patterns in the data. So another thing that you really should understand about neural networks and deep learning especially is that a deep learning model can be trained to fit anything, as we've already mentioned, as long as it has enough representational power, right? And in deep learning, it's easy to get plenty of representational power, adding more layers or more units to layers, things like that. So, this effectively means that you can always add enough representational power so that your model will be able to continue to lower the training loss as you train it, right? Even on completely random noise. Okay, so again, let's look at a quick example of that happening. Oops. So here we're going to train MNIST again, but we're not going to give it actual data. We're using the data, sorry, so we're still using the regular images, but we're just randomly shuffling the labels. So there's really actually no correlation between the shapes that are given and the label that we tell it is the correct label if we do it like this. Okay. So in this case, we're using the same model as before, 512 units in a single dense layer. So let's go ahead and let that train. Okay, once training finishes, let's go ahead and do our usual learning curve plots here. So these should look a little bit unusual to you. Training loss does keep going down after 100 epochs of training, and it's not quite as high as the accuracy. It is a lot tougher of a problem. The labels are actually random, but the accuracy is continuing to increase. If we kept training, it might continue to get its accuracy up above 90%, 95%. But the loss never goes down. In fact, it just immediately goes up on validation. And notice that the accuracy is at 10%, so just random guess level if you ask it to make predictions about data it wasn't trained with. So effectively, in this instance here, what's happening is the model has enough representational power that it's just doing rote memorization. So it's kind of like a fancy dictionary. It just completely learns the mappings between the inputs it's trained with and the outputs. But that doesn't, there's no information at all, though, that it can use to generalize to stuff that it hasn't seen, right? So the representation it learns is only a rote memorization of the input data that it's trained with, right? So, with that in mind, you might wonder, how can a deep learning model generalize at all, right? So when learning, just pure noise, like in this example, we're basically learning an ad hoc mapping, like I mentioned. But if you fight the overfitting that's happening there, you can actually learn a representation that you can interpolate from unseen stuff to the stuff you've seen and make informed predictions about what the class or what the value might be of the item you're trying to predict. So this is one way that you can understand how it is that deep neural networks are able to learn, okay? So just as an example, take the MNIST data set that we were just using. So the actual space of possible inputs is a huge number, more than I can't remember what they said in our textbook. More stars in the sky. It's a very large number. It's 256 raised to the power of 784. Right, because there's 256 possible values, since we have an integer that ranges from 0 to 255 for each pixel. And we've got 28 times 28, which is 784 of those pixels. Right, so that's a huge number. But very few of those inputs would look like a digit. So a exceedingly small fraction of that possible input would be something that would be like an actual digit that someone would write. So the theory, the manifold hypothesis, is that the actual digits occupy a tiny subspace, and it's not a random subspace. It's not spread randomly in that really extremely high dimensional space. So all the samples in the subspace are actually connected by smooth paths. So, you can find kind of a path that you can transform a 1 into a 2. And most of the things along that path would be things that might possibly be found as digits that people would write. Okay? So that's called a manifold. Hand digits, the theory is that they form a manifold within that larger space of possible inputs. So the manifold hypothesis posits that all natural data lies on a low-dimensional manifold within that higher dimensional space where it's encoded. Further, that manifold is smooth in some sense, right? So the points that are possible in the manifold are going to be connected. So that makes it possible for machine learning and deep learning to work. The models only have to fit a relatively simple low-dimensional manifold for that large subspace. And since it's smooth and continuous, so since the subspace seems to always be relatively smooth and continuous, it's possible to interpolate between any 2 points. And that ability to interpolate between sample points is what is the key to understanding this idea, understanding how generalization is possible in deep learning. Okay. So just a little bit, quick, more about the idea of interpolation. So interpolation is not linear interpolation. It's not averaging like 2 values in the encoding space, right? So usually if you take the average of 2 digits that are actual digits in the MNIST manifold, you'll get something that doesn't look like a digit, that wouldn't appear as something that people would naturally create when trying to write a digit. So the manifold interpretation is saying that the space lies along a smooth continuum. So instead, if I was modifying, a single pixels at a time, I could get an interpolation that would transform like 2s into 0s. And along the way, you might end up in spaces that are other things in the space, like 6s or so. So interpolation along a manifold is different from linear interpolation, and it can only help you make sense of things that are close to what you've done before. Okay, so this is kind of a limitation of what deep learning models can do, is they can really only recall stuff that they've been trained with. They can only interpolate from the manifold that they learn, and what you ask it to make predictions on has to be somewhere close so it can do that, so that interpolation will succeed. Okay, so we have this figure in a previous chapter. So, you can think of the affine transformations that happen in a deep neural network when it goes through the different layers as a way of uncrumpling a ball of paper. So that is, in terms of manifolds, that is that we're taking this and disentangling the latent manifolds that are present in the set of data that we're trying to learn. Okay, so a deep learning model is basically a very high dimensional curve that's smooth and continuous. It has to be, because in order to do differentiation our curves have to be continuous so we can calculate the gradients. And we fit this smooth, continuous, high-dimensional curve onto the data via gradient descent. So we do that incrementally, but smoothly transforming it so it approximates the manifold of the data that we're trying to learn. Okay, so this is in general how and why deep learning works. So, once again, the curve, that we're training in a deep learning model involves enough parameters that can fit anything, okay? So before training, we start with just random initial weights, so the decision boundary in this case is meaningless. So as we gradually train the model, it moves closer and closer towards a better fit. Then at some point, some intermediate point during training, the model roughly approximates the natural manifold of the data. So this is where we've reached the boundary where we're not overfitting yet. Kind of in here. So the final state, so what happens on a deep network is that it will start overfitting at that point. So it will start modeling outliers or some of the noise like we talked about in here, right? So at test time, so the performance, if your model was robust, so if you've done something to keep it from overfitting, we end up with a manifold that actually approximates the true manifold of the data that we are training with, right? So this will do well on classifying data that hasn't seen before, right? So this is kind of like that. We stopped training or did other things to fight overfitting. If we're overfitting, our model won't be as robust. It will have poorer performance. It won't be able to generalize. In this case, because we tried to fit, like maybe this is an outlier over here, we're going to be making mispredictions on things where we overfit to the noise or the outliers for the data that we have. And a final thought on this, training data is paramount, right? So it's very important in deep learning and machine learning, in machine learning in general. So this is kind of a good illustration of what people mean by that. So the power of a model to generalize is a consequence of the natural data structure in your data. So it's not really the model, it's the structure in your data. So having good data and feature engineering are essential for a model to perform well. But it needs to have a dense enough sample of the input space so that it can form a manifold that's a good approximation of the true manifold that you're trying to learn, right? So if our original latent space is like this, if we don't have a dense enough set of data points, the best a model can do is something like that. It's going to be poor on different things. But if you have enough data that you can fill in and correctly have the points that you're interpolating the manifold correctly or detecting the shape of the manifold correctly, you'll be able to get good generalization, right? And so, the best way, there's no way to get around it. The best way to improve a deep learning model is to train it on more data and on better data. Okay, so kind of just a few quick points in summary on this section here. So we were talking about generalization, so the goal of machine learning. So keep in mind that the fundamental issue in machine learning is the tension between optimization and generalization. Overfitting always occurs in a deep learning model. So you can always give enough representational power to a neural network so that it can fit anything, even just random noise, right? So it can essentially build up a dictionary or mapping by pure memorization of the inputs to the outputs. So the ability to interpolate between samples is the key to understanding generalization in deep learning. And it's part of the hypothesis of the manifold hypothesis that, these natural data forms continuous manifolds like that, which makes interpolation possible. So the typical thing when you're training with a deep neural network is that at some intermediate point during training, the deep learning model roughly approximates that natural manifold, if you've got a dense enough sample of your data that you're training with. And at that point, it will start overfitting. So for a model to perform well, it needs to be trained on a dense enough sample of its input space. All right. So that's it for this video. We'll be continuing on next time, talking about how we evaluate machine models in a little bit more detail. Hope that was helpful, and hope to see you all in our next video then.